Thank you, Gregor, for the introduction. Good afternoon, everyone, and welcome to my PhD defense presentation titled Modeling of Wind Power under Stressed Voltage Conditions. Firstly, I would like to go through the contents of the presentation. It starts with a brief introduction about the background, motivation, and research objectives of the PhD thesis. This is followed by wind power plant reactive power capability model development. Then we will look into support from wind power plant during stress voltage conditions. Now, wind power being fluctuating in nature, we will like to investigate into robustness of wind power plant as a reactive power source. Further, a probabilistic approach of voltage stability assessment is discussed in the light of wind power uncertainty. Finally, conclusions of the thesis are discussed. So, starting with the introduction, this PhD project has been part of Forskull project called Security Assessment of Renewable Power Systems, SAR. The objective of this project is to develop technologies for secure and stable operation of future power systems with high share of fluctuating renewable energy source-based generation. Now, secure and stable operation of power systems with high share of renewables poses challenges like low short circuit ratio, reduced reactive power resources, and increased uncertainty. There have been many blackouts due to voltage instability in past, which can be attributed to both long-term and short-term phenomena. Now, recent events like that of South Australia blackout in 2016 and the UK incident last year have led to increased focus on grid connectivity and potential integration issues of wind power generations. Now, most often, wind power plants are located far away and are connected to the grid through long AC lines. This makes the system at the point of connection weak, and the power system is more prone to voltage instability. However, there has been limited research regarding integration of wind power plant models for long-term stressed voltage conditions, which have led to many unmet needs. Well, one of the first challenges is that in future converter-dominated power systems, there will be reduction of conventional reactive power resources, which have traditionally been the synchronous generators. So, as the synchronous generators are being replaced by converter-connected wind power plants, the wind power plants need to provide reactive power and voltage support to the grid. However, the unmet need is that in order to perform voltage stability assessment and quantify reactive power reserves available, knowledge of wind power plant reactive power capability is required. This provides motivation for estimation of wind power plant reactive power capability suitable for large system studies. Now, when the power system moves into alert state from normal state, usually there are some preventive actions that are specified in order to mitigate the risk of voltage instability in the system. However, these preventive actions are mainly devised for traditional power systems. In future renewable energy sources dominated power systems, wind power plants need to support the grid during stressed conditions. Although some grid codes like that of continental Europe distinguish between normal and alert voltage ranges, there are no specific wind power plant control actions specified during alert conditions. This provided the motivation for development of wind power plant control strategies during stressed voltage conditions. Next, we know that wind is a fluctuating resource. Therefore, accurate estimation of reactive power in future rest-dominated systems is a challenge. There is a need for reactive power capability estimation of wind power plant considering fluctuating nature of wind. This provided motivation in assessing the robustness of wind power plant as a reactive power source, considering uncertainties due to fluctuation. This fluctuating nature of wind also possesses challenges in terms of voltage stability assessment of the system. Now, traditional voltage stability assessment techniques only consider changes in loads, but now the generation resources are also fluctuating. Under stressed voltage condition, effect of wind power fluctuation may move the power system operating point beyond the stability margin. Therefore, voltage stability assessment techniques, including the wind power fluctuation, are needed. This provided motivation for integration of wind power fluctuation in voltage stability assessment methods. Now, these challenges and motivation led to the formulation of the following PhD objectives. Firstly, how to estimate reactive power capability of wind power plants suitable for large system analysis in terms of parameters required and computational complexity. Secondly, how should wind power plant be controlled in order to provide maximum support to the grid during long-term stress voltage conditions? Should conventional wind power plant control strategies, which are meant for normal operation, be extended during stress voltage conditions? Or can the voltage VAR support from wind power plant be enhanced in order to provide support beyond the conventional strategies? Thirdly, how to assess the robustness of wind power plant as a reactive power source, considering uncertainties. How to quantify the robustness of wind power plant reactive power capability due to uncertainties like wind fluctuation, technical availability of wind turbines, and discrete control action of the wind power plant transformer. Fourthly, how to integrate wind power fluctuation in voltage stability assessment studies. What is the impact of wind power fluctuation on voltage stability assessment? So this PhD work seeks to answer these research questions, and with this, we come to the reactive power capability model of wind power plants. So before going into the reactive power capability model for wind power plants, we would like to develop the model for wind turbines. So here, if you can see my cursor, this is the schematic diagram of type 4 wind turbines with full rated converters. Typically, in type 4 wind turbines, the reactive power is supplied by the grid side converter, and it is mainly dependent on the grid side converter parameters. The two main limiting factors are converter voltage and converter current. We can see here that the wind turbine is connected to the wind power collection grid through a step-up wind turbine transformer. Sometimes there can also be filter or impedance in between the converter and the transformer. And so in order to develop the wind turbine capability model, what we can do is we can aggregate this area, this portion of the circuit into a simplified wind turbine equivalent representation as shown here. And then using this equivalent wind turbine representation, we can find the converter voltage limited reactive power as given by this equation, and the converter current limited reactive power given by this equation. And we can see here that both these reactive power equations are dependent on the active power production from the wind turbines as well as the collection grid voltage here. And of course, they are limited by the two limiting factors, maximum and minimum converter voltage and maximum converter current. So here to demonstrate those reactive power, converter voltage limited and converter current limited reactive power, we see here that the red curve here shows the voltage limited reactive power, while the black one here shows the current limited reactive power. And at any operating point, we can see that it is the reactive power capability is either voltage dependent or current dependent. And the region here, the gray region here, is the actual reactive power capability of the wind turbine. So this can be obtained from the equation shown below here. So if we draw the active power and voltage dependent reactive power capability, we get something like this, where each of these colors represent a typical specific voltage level. And we can see here that this red one is for low voltage, 0.9 pu. And we can see if correlating with this graph here, we can see that this at low voltages, the reactive power capability is mainly converter current limited. Whereas for high voltages, as for example in this pink curve, it is mainly
the capability is mainly converter voltage dependent. And also we can see that the capability curves are non-linear in nature. So when we have the wind turbine capability curve, we extend the same model in order to get the wind power plant capability curve. So in order to extend, what we do is we include the aggregated collection system model derived using the topology and the collection system parameters of the wind power plant. So the aggregation is done using the paper mentioned in the footnote here. And this includes the series impedance and shunt capacitance of the whole collection system. So the losses in the system are preserved in this model. The assumption here is that all wind turbines produce the same power. So any spatial variation in wind speed due to variability in wind and wake effect are neglected. So here is the active power and voltage dependent reactive power capability for wind power plant. It is similar to the one seen before for wind turbine, only that it is a bit reduced because of the losses in the collection system. Now, if we use detailed wind power plant model in order to calculate the reactive power capability, we'll get most accurate capability curves. However, the detailed model requires lots of parameters, and also like inclusion of hundreds of detailed wind power plant models for large system studies may not be feasible. On the other hand, if we use the wind power plant capability obtained from scaling of wind turbine capability curve with the number of wind turbines present in the wind power plant, then it will require less parameters, of course, but the collection system losses are neglected. So our proposed methodology or the proposed capability model, it requires both less parameters, less computation time, while being accurate in estimation of capability when compared to the scaled wind turbine models. So to compare the performance of the proposed model, we take the detailed wind power plant capability model as the base case, and then we choose 3 wind power plant topologies as seen here. So the case 1 is a wind power plant with 7 wind turbines in a string. Case 2 is Hallstorf 2 with 91 wind turbines. And case 3 is Borbo-Bank, which has long collection system cables. So next, what we do is we find the average root mean square error of the capability obtained from the scaled wind turbine compared to the detailed, and as well as for the proposed model. So here on the left-hand side, we see the average root mean square error for the scaled model, for the error between the scale model and the detailed model, and we can see that the error can go up to 11%, as in the case seen here. However, for the proposed model, when we compare, we can see that the errors are much less. The highest one here becomes less than 4% in the case of the proposed model. So the proposed model can estimate wind power plant reactive power capability with high accuracy, less than 4% error, as opposed to the predominantly used scale wind turbine model, which has more than 10% error. So from now on, all further studies done in the thesis will be based on this proposed wind power plant capability model. Next, we look into the voltage and reactive power support from wind power plants during stressed voltage conditions. So for this purpose, we use the network model as seen here. So it is a simple 4-bus model with an external grid, load, and an aggregated model of wind power plant, similar to the one described earlier. Now, this aggregated wind power plant model is connected to the grid through a tap changing wind power plant transformer. Now, the main the voltage at the WPP voltage, the voltage at the point of connection of WPP, is maintained by the tap changing actions of the wind power plant transformer. Typically, it is maintained at 1 pu, and the PCC voltage is being monitored in order to detect stress in the system. So when the PCC voltage goes below a predetermined threshold value, one of the control strategies is activated. So firstly, we look into the conventional wind power plant control strategies as described in the grid codes: reactive power control, voltage control, and droop control. Well, as mentioned before, none of the controls, no specific control action from wind power plant is specified during stress condition. So here we assume that the conventional control strategies as described during normal operation will be applied during stress condition as well. So with this in mind, we do sensitivity study for Q control strategy for different values of reactive power references. And we compared the results with the base case of zero reactive power support, that is unity power factor control. So there is no exchange of reactive power between the wind power plant and the grid. And we can see here that if we provide maximum support when the grid is during stress voltage conditions, the PCC voltage increases as expected, but there is a kind of a sharp change in voltage due to the step change in reactive power support here. However, we can see that if we provide maximum reactive power as seen in the PV curve here, if we provide maximum reactive power support during Q control, then the maximum power transfer of the maximum power transfer capability of the system increases by 10% when compared to the base case. So next we go into the droop control strategies. Here also we did sensitivity study for different values of droop, 4%, 6%, and 8%. Well, if you see the performance of the three droop values or of the three cases, then you see it is more or less comparable. Only the difference is that for lower droops, the reactive power capability limit is reached at a lower nominal load. However, if we compare it with the previous Q control strategy, we can see here that the maximum power transfer still remains the same as in the case of Q control strategy. Next, we go into voltage control strategy. Here also we did sensitivity study for different voltage set points. So we see here if the voltage set point is greater than the threshold value, which is this one here, then what happens that there is a steep increase in the PCC voltage. However, if we set the set point at the threshold voltage, then the PCC voltage is maintained at 0.95 until the wind power plant reactive power capability is reached here. Again, when compared to the previous two strategies, it gives the same maximum power transfer, and that's mainly because in all three cases, maximum reactive power capability limit of the wind power plant is reached. So this motivated us to investigate into enhancement of this capability in order to provide better support to the grid. Now, as discussed previously, the wind power plant capability is both active power and voltage dependent. So if we choose a constant active power, any operating point, and see the relation between the voltage and the reactive power capability, then we can get something as shown in the figure here. We can see here that as the voltage increases, the reactive power capability increase, but then after this point, it starts decreasing with increase in voltage. Therefore, if we can find this value of maximum reactive power and the corresponding voltage at which it is obtained for a particular operating point for a particular active power production, then what we can do is we can modify the wind power plant voltage, POC, the point of connection voltage, using the wind power plant trap changing transformer and enhance the reactive power capability of the wind turbine. Now, in this study or in the thesis, I have used this enhancement along with, in conjunction with the voltage control strategy. However, this can be easily applied with the Q control and droop control strategies as well. So looking into the performance of the proposed strategy, this is the initial condition where the PCC voltage is greater than the threshold voltage and the wind power plant is controlled at unity, so zero reactive power from the wind power plant. Next, what happens is the PCC voltage goes below the threshold voltage, and our enhanced proposed control strategy is activated. So what it does is that it sets the PCC voltage to a set point of equal to the threshold voltage, and the wind power plant voltage set point is changed to 0.93 according to the reactive power capability and voltage relation shown in the previous slide. So with this, we see that the reactive power capability increases here. Next, what happens is the taps of the wind power plant transformer gets limited. It reaches maximum limit. Therefore, the wind power plant voltage cannot be maintained at 0.93 pu, and it starts to increase as seen here. However, we see that the PCC voltage is still being maintained at the set point. That is because the reactive power requirement in order to achieve that voltage is still less than the reactive power capability of the wind power plant. In the next, in all these cases, we have simulated the load is continuously increasing in the system. So with further increase in load, what happens? The reactive power capability limit of the wind power plant is reached, as seen here. And as a result, VPCC can no longer be maintained, and it starts decreasing due to increase in load. And consequently, the wind power plant voltage also starts to decrease. However, we see that the tap changing transformer is still limited on its maximum limit. As the load further increases, what happens is the PCC voltage continues to decrease. As a result, the wind power plant voltage now reaches 0.93, which was the set voltage from our proposed control strategy. So when the wind power plant voltage reaches 0.93, the tap changer limit is released. It's no longer, the taps are no longer saturated, and the reactive power capability now becomes constant, and the voltage at wind power plant is maintained at the set voltage. So when we compare the conventional, when we compare the proposed strategy with the conventional strategies, we see that we get an increased maximum power transfer capability. An additional 5% improvement is achieved from this when compared to the conventional control strategies. And also, as I mentioned before, this can be applied in combination with Q or group. So it requires no, this strategy requires no additional installation of any additional resources. So to investigate the feasibility and effectiveness of all of the proposed strategy, as well as all the control strategies that we did here in a large realistic power system, we implemented all the control strategies in the Hellenic interconnected system, and we see from the results here, they are similar to the 3-bus systems. We see an improvement of maximum power transfer when using the conventional control strategies during stress voltage conditions. However, the enhanced capability-based voltage control performs better and helps in alleviating voltage instability better than the conventional control strategies. Next, we will look into robustness of wind power plants as a reactive power source. So in order to quantify the robustness of wind power plant as a reactive power source, we take into account 3 uncertainties. Well, for the first uncertainty arising from the discrete voltage control action of the wind power plant transformer, the second one arising from the wind power fluctuations, and the third one arising from the technical availability of wind turbines. So dealing with the uncertainty with the discrete voltage control action first, we know that the taps are discrete in nature. So the voltage set point of the tap changing transformer can vary between an upper and lower bound. For example, if the voltage set point is 1 pu, and there is a 2% voltage regulation, then the upper and lower bounds of the voltages will be 0.99 pu and 1.01 pu respectively. Now, if we draw the reactive power capability as shown in the figure here, for these three voltages, then we see that the reactive power capability due to the higher voltage is the most restricted one. Well, it will be different in this is the case in case of reactive power injection. If it's reactive power absorption, it will be reverse or opposite. Anyways, so in order to have a conservative approach to deal with the uncertainty due to this discrete voltage control action, what we do is we proceed with the worst case, the most restricted reactive power capability of wind power plant and do further studies. Here we can see the fluctuations in reactive power with respect to fluctuations in wind power. Now, it looks nice, but it is difficult to understand. And in order to understand and quantify these reactive power capability fluctuations, we used ramp. This is an example of a ramp for calculated for time period of 30 minutes. So here the black upward arrows denote positive ramp values, which indicate that the reactive power capability of wind power plant is increasing. The downward facing black arrows, they denote negative ramp values, which means that the reactive power capability is decreasing. Now, during stress voltage conditions, we are more concerned about decreasing reactive power capability. So in order to quantify these capability ramp, we use the duration curves, and we are mainly concerned about these negative ramps. And we can see here from the graph here that the worst case negative ramp, which is around this region, keeps on increasing with increase in the time period of study. So now that we got the fluctuations, we would like to include both fluctuation and availability. And therefore, to have them both, we define a wind power plant robustness index, which is defined as the ratio of reduced reactive power capability due to fluctuations and availability to the nominal reactive power capability for a given active power production. Now, the total robustness index, or the WPP robustness index as I call it, is a combination of robustness index due to fluctuation and availability. However, we can also find these values separately. Here is an example of the robustness index, which is calculated with 90% availability and including 95% of wind power fluctuations. We can see here that the robustness index is decreasing with increase in time period of study. And in case of 30-minute time period, we see that around this 0.6 pu active power, the robustness index is around 0.54, which means there can be a loss of up to 46% of wind power plant reactive power capability in case of 30-minute time period. So, the same in case of 10-minute time period, we see that there can be a loss of about 33% of wind power reactive power capability. However, for a shorter time period, well, the wind power plant can act as a reactive power, robust reactive power source. Therefore, the choice of time period is very important when we are using wind power plant as a reactive power source. So if it is being used for shorter time period, fine. But if it is used for studies which involve longer time period, then the uncertainties arising out of fluctuation and availability are required to be included. Now, we got the robustness index in the previous slide, and with that robustness index, we modified the capability curve for the 3 different time periods. And we can see here, as expected, the 30-minute, the capability curve for 30-minute time period is the most restricted one. And then what we did is we included this reactive power, this restricted or modified reactive power capability into the four-bus power system as described earlier, and we studied the impact of reduction in robustness on power system. So the black curve here represents the robustness index of 1. That means none of the uncertainties are included in here. So we see that with this, we get a maximum power transfer of 1.42 pu here. However, as we include the robustness index, as in case of this red curve here, the red one here, we see that the maximum power transfer has reduced to 1.36. So there can be 4.2% error when not considering robustness index of wind power plants. However, we can see that the reactive power support from wind power plant is still beneficial as opposed to the zero support, as in the case here, even with all the uncertainties involved with the capability and due to the fluctuating nature of wind. But it is to be remembered that the reactive power capability can be substantially reduced for longer study time period due to uncertainties. With this idea in mind, we move on to the probabilistic voltage stability assessment. In the last slide, we saw that the maximum power transfer, which was the voltage stability index for us, was being impacted by the fluctuation in wind or fluctuation in reactive power capability. So what we try to do here is we try to assess the error due to neglection of fluctuations in wind power. So what we did is we calculated the voltage stability index with the last wind power measurement values, that is the persistence values of wind power. And then we calculated the voltage stability index with the actual values of wind power. And then when we do the error analysis, we see that the from the cumulative distribution of error here, that there is a 38% probability that there will be overestimation of the voltage stability index if using the voltage stability index based on persistence. So this led to development of two methodologies for calculating probabilistic voltage stability index. The first one is using the variations in wind power. Now, we know that wind power can increase or decrease between 2 consecutive time periods, and depending on the conditions, the increase in wind power may either increase or decrease the voltage stability index. So what we do is we divided this methodology into 2 phases. One is the offline phase, and the other one is online phase. So what we do in the offline phase is that we compute the probability distribution matrix, something like this shown in the figure here, for the wind power based on the historical data of wind power for a particular geographic location. And then during the online analysis, what we do is we look into this probability distribution matrix and we find the maximum and not maximum, but the upper and lower values of wind power based on the value of risk that we want to include in our study. And then using these 2 values, we calculate 2 voltage stability indices, and the minimum of these 2 voltage stability indices gives us the probabilistic voltage stability index. If we see the results here, so the black one is the actual voltage stability index, and the red one is the probabilistic voltage stability index calculated using our methodology. And we can see that for most instances, the predicted probabilistic voltage stability index is less than the actual voltage stability index. If we look into the error between actual voltage stability index and the probabilistic voltage stability index, then we find here that the probability of actual voltage stability index being less than the predicted value of the probabilistic voltage stability index is less than 5.5%. So 94.5% of the time, this probabilistic voltage stability index can be used for planning of uncertainty on power transfer capability. The second methodology involves using variations in the voltage stability index directly. So voltage stability index is varying between 2 consecutive time periods. So in the offline phase, what we do is we calculate the voltage stability index for each active power production for a particular for a particular system power system configuration, and we get a relation something like this here, shown here in the graph. And then what we do is we use the relation in order to compute the probability distribution matrix for the voltage stability index, as shown in the figure here. Then during online analysis, in order to calculate the probabilistic voltage stability index, we use this probability distribution matrix, and based on the current value of the voltage stability index, we look up the risk of decrease of voltage stability index, because we are more concerned about the decrease in the voltage stability index because of stress conditions. So again, looking into the results for this methodology, we see something similar, but now in this case we see that there are fewer values of VSI which are less than the predicted value. And if we do the error analysis again, we see the probability of the actual voltage stability index being less than the predicted value is less than 4.1%. So both the proposed methods give significantly higher confidence in the voltage stability index as opposed to the 38% error in the persistence method. Well, the second methodology somehow is a bit better, but the computational complexity involved with this, with the implementation, especially on large power systems, may make it less preferable when compared to the first method. So with this, we come to the conclusions of the PhD thesis. At the beginning of the presentation, I started with some research questions. Now we would see how we try to answer those research questions. So the first question was how to estimate the reactive power capability of wind power plants. So in this PhD work, a novel wind power plant reactive power capability estimation model was developed. And this model requires less parameters, requires less computation time when compared to the detailed model, however, while having higher accuracy as compared to the predominantly used scale wind turbine model. The second question was, how should wind power plant be controlled to provide maximum support to the grid during long-term stress voltage conditions? So we see that using the conventional wind power plant control strategies during stress conditions helps in substantial improvement of the grid voltage as compared to the base case of unity power factor control. Also, a novel enhanced reactive power capability based voltage control methodology is developed, which provides additional grid support as compared to the conventional strategies. So we also verified these control strategies in a large realistic power system, and from that we can say that a wind power plant can take up an important role and can be a useful choice for voltage support during stress voltage conditions in future power systems where there will be reduced reactive power resources. The third question was how to assess the robustness of wind power plant as a reactive power source considering uncertainties. So a methodology was developed in order to quantify robustness index of wind power plant as a reactive power source. It included uncertainties like wind power fluctuations, technical availability, and discrete voltage control action of the tap changing transformers. Well, we saw that uncertainties can reduce the robustness of wind power plants substantially, especially for longer study time period as opposed to the shorter time period. So that makes selection of an appropriate time period necessary in order to yield higher confidence in wind power plant as reactive power source. We also saw that the reduced wind power plant capability can lead to overestimation of voltage stability margin, which can be critical under stress voltage conditions. And that brings us to the answer of the fourth question: how to integrate wind power fluctuation in voltage stability assessment studies. For this, we developed two probabilistic voltage stability assessment methodologies, where the uncertainty in the voltage stability index is quantified, and the uncertainty and the uncertainty is quantified through propagation of uncertainty from wind speed to wind power to reactive power capability to the voltage stability index. Also, we saw that the probabilistic voltage stability index exhibits significantly better results in predicting voltage stability bounds as compared to the deterministic values. So maybe in future power systems where we'll have lots of fluctuating resources, maybe we will move into calculating probabilistic bounds on voltage stability index instead of having a deterministic value of voltage stability index. So to summarize the PhD, I would say proactive support from wind power plants during stressed voltage conditions, utilizing wind power plant reactive power capability can alleviate long-term voltage stability. However, probabilistic approach in the view of fluctuating nature of wind power plant is required in order to yield higher confidence in security assessment of renewable-based power systems. I have listed a few future work which can be extended from this PhD work. Well, some of these I started during the PhD, however, due to limited time in the PhD, I couldn't complete it. And some of them were planned during the initial planning of my PhD, like the verification of the control strategy in a research facility. Well, because of some unforeseen reasons, this wasn't possible to do it. But I have just listed them here, and maybe we can take it in details later if needed. I would like to mention that this PhD, in this PhD, we managed to publish 3 journals, 3 conference papers. 2 of the journal papers are under review. One of them is being prepared right now. It will be submitted. And there were 2 other publications which were done during the PhD, but are not related to this PhD project. Finally, I have a few seconds, and I would like to take those few seconds to acknowledge. Firstly, I would like to thank my supervisors, Professor Paul Sorensen, Dr. Anka Hansen, Dr. Mofet Altin, and Dr. Jortur Johansson for being my supervisors. I would like to thank my assessment committee, Professor Nikolaos Koutouloulis, Professor Bikash Pal, Professor Damien Flynn. I would like to thank Dr. Gregor Gibbon for being the chair of this PhD defense. I would like to thank Professor Kostas Vonas for hosting me during my external research stay at National Technical University of Athens. I would like to thank Dr. Matti Koivisto and Dr. Peter Maule for helping me with the chorus results. I would also like to thank Dr. Batia Jan Karatas and Dr. Theodoros Success. I would also like to thank the funding agency, Forscan, my SARC colleagues, my colleagues at Integration and Planning section. Thank you, DTU Wind Energy. And finally, thank you, my family and friends, for being supportive. Thank you.
So this is, in real proceedings, this would be where we all clap. In these proceedings, it's a bit different, obviously.
Unmuted.
And thank you, Moumita, also for excellent timekeeping. And I would suppose we do about 5-minute break and then reconvene here for the second part of the proceeding.
Okay.